it's my pleasure to introduce Sione Mau from New Zealand, Auckland, University of Auckland, who will speak about Akunkov bodies and something.
And something. Okay.
Oh, how should I forget about it?
Yeah. Anyway, thanks for organizing this conference, Vanya. It's a pleasure to be invited to speak here. Okay, and so I'll eventually get to these things closer to the end of the talk. My field is actually potential theory and several complex variables of potential theory, but there's some interesting connections here with things in algebraic geometry. But because I'm working more in several complex variables, everything is sort of in Cn. And the context will be any variety I'm looking at. So work on a variety, it's always going to be a subvariety of Cn and smooth and everything. And we'll say smooth across the hyperplane at infinity in Pn. Okay, so we're taking this thing and let's look at polynomials on the variety. So start it like this, and we'll be looking at polynomials of say degree up to k, and this means here that I'm looking at sort of restrictions of polynomials of degree k in Cn. On the variety here. Okay, so what I'm going to do now is we're going to look at polynomial evaluation, but with weight. So what's a weight? Basically, it's a continuous function, let's say. Continuous, and really we'll be looking at phi being minus the log of this weight, and this thing will be plurisubharmonic, but you don't have to know what that means. So we'll just write e to the minus phi. It's basically w here, and we'll think of. We'll be looking only here at these things called admissible weights, which have the property that as z goes to infinity in absolute value, so every absolute value here is just taken up here, right, in Cn. Then it's got the right that goes to 0. I'm supposed to say. Okay. And then we can look at a way to evaluate polynomials. So I'll just call it a weighted polynomial evaluation, where you just evaluate this polynomial and then you just throw in this weight here. So, so if you're in spatial polynomials of degree up to k, we'll put an e to the minus k phi of z, like that. Okay, so this thing is, this affine thing is sort of, you can think of it also as a Hermitian metric. I'll just say here related to Hermitian metric. If we just write pz e to the minus k pz, say q, consider this product here, right? E to the minus k pz to the bar here. you can think of that if you think projectively, everything is okay across infinity. So therefore, that's the relation with the permission metric on sort of the the line bundle listing restricted to V. Okay, but I'm going to just be thinking of it as a weighted polynomial evaluation on variety there. Okay, so once we have this weight or this, if you like, permission metric, then we can look at some norms on this space, this vector space here. So first of all, we can look at the following type of inner product. So if we're given, say, a probability measure, mu supported on this variety here, then we can think of an inner product where we'll write, so everything here, again, we're thinking of fixing the k, and then I'll write subscript here, k phi mu, and that's going to be this inner product given by just integrating this thing with respect to mu. Okay, so p e to the minus phi q e to the minus phi bar, with a k here. Okay, so that's important, the mu. And then, of course, you can go from here to look at sort of the L2 norms. So we'll also look at a notion of a subnorm on a set. As well, so given us.
So is it for polynomial degree less or equal to k, or?
Oh yeah, less than or equal
less
to
or
k.
equal to k. So therefore you have kind of infinite. Okay. So you have kind of infinite set, yes? Infinite set of spaces. Hermitian.
Infinite set of spaces, yeah.
Okay.
And each of them has one. Yeah. Okay, so now given, so this is like capital K, a set. And you can also look at subnorms of these. So I'll write it, say, P, so again, little k phi, but the subnorm on k will be, the usual thing, you just plug in this thing. That's right. Sub over k, p e to the minus k phi. Okay. So there's that. Okay, so so it's a trivial thing that if the support of mu is in k, then you have this thing less than or equal to this thing, right?
So k is a compact, yeah.
Compact, I just say closed.
Closed, okay.
Doesn't matter at this stage, but later I'll take it compact, yeah. Okay, so if the support is in k, then you have, so this is just automatic. So the integral is less than or equal to the sum, basically. But
it is decreasing, yes? So when we take bigger space, bigger k, it's decreasing, yes? For a given polynomial.
what's the decreasing these norms?
Yes, yes, so it goes down. When you embed to a bigger, yes? So what normally happens? You have a polynomial of degree k, you start to measure it with bigger kind of polynomial. It's going down, that's my impression.
Right.
Cavity, right.
Yeah,
So it goes down, yes, but it doesn't go to zero. That's okay. Can it go to zero simply?
I think Yeah, so if you're saying fix a polynomial, but
Yes.
you're letting k go to infinity.
Yeah.
Yeah. I think I will go to 0. But we're going to be thinking of these things, sort of the space of these things, and usually the important elements will be sort of the higher degree things.
Oh.
Yeah. Okay, but so for fixed k we get that, and okay, so an important property here is called, so I write Bernstein-Markov. Property, which is the following one, is that you can get sort of a reversed inequality, but with some constants thrown in. So that means, so that's defined to be so usual analysis for all epsilon bigger than 0, there's some uniform constant c, okay, which is independent of k. So this inequality is independent of k, such that
Okay, capital K. Or
Small k.
small k, so small k is the index.
Degree.
Yeah, the degree of these polynomials. Yeah. Independent of k, little k, such that you have an inequality going the other way up to a constant, say 1 plus epsilon, 1 plus epsilon to the power k here, little k, and then the L2 thing. So Kc. So this is a Bernstein-Markov property. So it's a property of sort of this triple here, where you have the k, the weight, and the mu. Okay. So if you have these three things and this property holds, then the Bernstein-Markov property. So basically, well, for any set and say continuous weight, pretty much any measure you can think of will have the Bernstein-Markov property. It's sort of, to get something that doesn't is possible, but those are sort of pathological things. Okay, so from now on we'll assume everything has this property here. So what does this mean in particular? So say, it means that if you have, say, a sequence of polynomials, and then
this is another K though, is it?
yeah, so now, so if you have a sequence of polynomials k, so now k is the index, and we're going to think of these sequence of polynomials, each member being in this
Of
set of
degree
polynomials.
less than k.
Yeah.
Less than k.
Yeah. So basically think degree k. So then just by doing some analysis, you can see that if you take this limit here, you take the kth root of this thing, if that goes to some limit, if and only if the L2 thing also goes to the same limit. Okay, and then this Bernstein-Markov property is sort of important in, well, sort of used everywhere. Okay. So that's a Bernstein-Markov property. So now we'll go on and look at all volume ratios. So again, staying in space here. What we can do is we can think of different sets and different weights and putting sort of different inner products on this space here. So let's have a look at one weight and one measure. And we can also look at, so this thing will give us, you know, sort of that thing, and then we can think of another oops. In that form. And then, yeah, so later we'll look at orthonormal bases with respect to this inner product here and L2 thing. So let's just write this one by, say, e to the, I'll just write phi, the weight for indexing that. Okay. And then we'll look at taking balls with respect to these L2 norms. So let's write, say, B2 so those are all the polynomials of norm, say, k theta mu less than or equal to 1. And similarly, you can think of the L2 ball of the other one. Okay, so now let's define this functional here, which depends on so these balls here. So, well, so any of them depend on, say, the phi and the mu weight. And this one, and it's going to be defined this way. N factorial over k to the n plus 1 times the log of the volume of, say, the top volume of, say, of this top ball over the, basically the ratio of the volumes. So B2, I'll just write phi and C here. Okay, so I'll just give a little example of a calculation with these volume ratios. There's sort of paper of Nystrom. So for example, if you let mu equal nu and it's equal to phi plus 1, then you can write out this volume here. So first of all, just by calculating the L2 thing, if you look at k phi plus 1, this L2 thing, that's equal to, it's just got an extra exponential to the k, so it'd be e to the minus k times, well, it's the same measure here, so we'll just so when you take the volume of the ball of this one, that's equal to well, so the dimension of the space is basically the dimension of that. So we'll call we'll just write m sub k for the dimension. Okay, so when you take the volume of a ball here, you get out an extra power of the dimension, right? So m sub k times p. Sorry, what am I writing? I mean, when you take the volume of this ball, it's sort of the volume of the ball of these things, but because it's dimension mk, it's so you get a factor there. Okay, so basically taking logs and taking volumes on that side. Yeah. Well, so this thing comes over here as a mk, and then we have k to the n plus 1, an extra k here, right? So you can see with that thing, as n goes to infinity, you get, sorry, as k goes to infinity, you get this well-known volume of so I would say sort of the line bundle O1, restricted to V, think sort of projectively, right? That thing. Okay, so you basically get you can see the limit, what the limit is in this case, and in general, there is a limit for any general pair of weights and metrics. Yeah, so this was a big theorem of Berman and Buxom. So this sort of Lk, as k goes to infinity, it goes to this, so I won't even write down what it is, but let's write, it's a sort of Monge-Ampere energy, so involving Monge-Ampere sort of powers of, say, DDC of, what do I write? Sorry, let's write it this way. So I write P sub k of P sub L of, see, let me just explain what those are. So if, so here, mu would be a Bernstein-Markov measure. I'll say that the triple, say, k, phi and mu would be Bernstein-Markov. So this k is the one that turns up in here. And for the second one, that would be the measure of mu appearing in the second volume down here would be Bernstein-Markov with respect to, say, this set and this weight here. And these things here are they're sort of like Green's functions associated to the sets. So they're sort of weighted Green's functions. On the support of the measure, they look like phi, and away from it, they're sort of the analog of harmonic, or in several variables, it's maximal plurisubharmonic. Okay, so that's the big thing in pluripotential theory. We're going to come to the Okunko and Chebyshev transfer in a moment. But first of all, we'll just note this this fact that these ball volume ratios can be written as a determinant, and that's sort of a change of variable type formula. So that's right. B2 phi B2 of C here. Okay, so let's come back to this thing. Because this is a finite dimensional vector space, and you've got sort of two Hermitian, sort of like, well, two inner products on this finite dimensional vector space. So the ratio of the volumes is related by a change of variable, which is given by a Graham determinant. So it's basically you take the inner product of, with respect to the first thing, so E of these phis, phi j, E phi, say, I shouldn't use K here, let's use L. Oh, sorry. You take the inner product of these things with respect to this inner product here, so let's get that right. So this orthonormal basis with respect to the change of basis matrix here, with respect to this thing. And then there's a power half here, okay? And then this formula will be that formula will be read with transfinite diameter. Let's see how much time we got. Okay, so where we're at, we looked at these ball volume ratios, Bernstein-Markov property, coming to transfinite diameter, and after this we'll see the connection to the Okunko-Bodson and Chebyshev transform. Okay, so what's transfinite diameter? So if you let, say, Ej be a basis of say all the polynomials on V. Okay, so we're going to enumerate these according to a graded order. So if you take say the first mk, you get a basis for this thing. This thing would be k. Then you can define so-called nth order diameters. So little k here, big K, and that would be the maximum, say, or the sup over mk points, mk the dimension. And let's say we'll take here K compact. And, So you take this basis and you evaluate it, this, and you basically take a van der Waals determinant and try and maximize its determinant over a set of points. And you take a 1 over kmk root. Okay. Right. This determinant is defined using a max or sup, and this one is defined using this L2 product. Okay, so I'll just say here, using Bernstein-Markov property, these two things have the same asymptotic behavior. So as long as this basis here is a basis, these EJs are the same as these ones, right? So you can
It is a orthogonal basis. EI is a orthogonal basis.
Yeah, okay, so when we're defining this thing, you can use, this just makes sense for any sort of, this basis here, then you can sort of relate these two determinants by this Bernstein-Markov. So I'll just say if EJ is from, star, that formula, then so then what happens at so the limit as k goes to infinity of this thing so is the same. They have to a factor of 2. Yeah. So I'll just write the same here. I mean, there's some different constants going on, but in the end, there's sort of like well, the same. I'll just leave it at that. Okay. So that's the relation with transfinite diameter. It goes to the Bernstein-Markov property. Okay. And now coming from transfinite diameter, we can finally get to the topic of the talk here. So how do these Okunko bodies arise naturally when you're trying to look at transfinite diameter here? Okay, but let's I'll just first define these things just using local coordinates in a kind of a simple way. So if we fix a point in V, and then we can consider, okay, so here we're in the, we would say fix the K here. We can consider writing P as a local, if we write it as a local power series, and I'll give an example in a moment, a very simple one.
The point, near point.
So here's our variety, just fix a point.
Yes. And nearby you write polynomial principles.
Yeah.
Okay.
Just expand as a power series. So yeah, give an example in a moment. So just sort of basically expanding about that point, and so that nu p be the sort of the trailing exponent here, so the smallest alpha. And when I say trailing term, I mean, of course, these are several variable things, so you have to put some monomial ordering on these things. So we'll put,
Yeah, okay.
yeah,
Lexicograph, okay.
lexicographic, yeah. So the lexicographic order where, say, yeah, so Z1 less than Z2 less than whatever the dimension is in this local power series. Okay, then I'm going to look at all the exponents for k here. So we'll say n sub k being all of these things, right? UP where all possible, right? Possible things. Okay, then we can think of rescaling them by say 1 over k, and we can take the convex hull, so the closed convex hull of all of these sort of integer, scaled integer points here. Okay, then the Okunko body is what you get when you take the closed convex hull of the union over all k's of these things.
Union.
Okay, so you take all of these
Yes, okay.
yeah,
No,
sets.
it's okay. It's, you just look at different directions and take minimum and maximum output.
Yep. Okay, the thing is everything depends on your points and your coordinates and whatever you choose here. Okay, so here's a cute example. So we can compute gamma for, so suppose we take the sphere here. Then we can take, say, the point 0, 0, 1, and then of course we'll take Z1, Z2 being our coordinates, and then here Z3 is sort of, I'll just say 1 minus Z to the half, and when you expand it as a power series, it's well, so you have 1 minus, say, from the binomial series, half Z squared, plus higher order things, and eventually we won't really need these things to compute the body. Okay, so when we start to compute this thing, if we start with, say, n1, okay, so it'd be important here that the number of points in nk, so it's sort of easy to see it, it's sort of the dimension, right? So you can just use this vector to compute these bodies. So n1, you know that it's spanned by, say, 1, Z1, Z2, and Z3, so linear things, right? Okay. So you get 1 point corresponding to 1, 1 corresponding to Z1, 1 corresponding to Z2, and then of course you've got Z3 here. But you can see the trading term of Z3 is 1, right? So therefore, because it's the same as 1, you can just cancel terms off by taking sort of linear combinations. Okay? And you can get another point. So Z3 minus 1, and then so the trading term now is this thing, and that gives you the point 2, 0. And you got 4 things, you got 4 points, so that's N1. It's done. But if you think of a clever way of multiplying polynomials, if you want to go up to N2, all you got to do is you got to throw in, so for N2, you just have to throw in the right number of quadratics, okay? So there will be, say, linearly independent things, Z1 squared, Z1, Z2, Z2 squared, Z1, Z3, Z2, Z3. But Z3 squared is linearly dependent, so it's not part of that. So you basically just need 5 more things, and all you have to do is look at this picture and say how can you get 5 more points, and that's it. Okay, so this is say Z3 minus 1. So you can get 5 more points this way. If you take this point, to get a quadratic, you multiply this polynomial by Z1. That's another point. You multiply this one by itself, and then the trading term is up there. You can do the same thing up here, right? Multiply by Z1, multiply by Z3 minus 1. But you can also go up here and you can multiply Z2 and get Z2 squared, you get another point. 1, 2, 3, 4, 5, and that's everything, right? And from there you can just see that, yeah.
So for products, you have products of the, you may have summation of the, let's say, of these convex different polynomials. Yeah. That's approximately like that. Yeah.
Yeah.
Okay. So that's what you're writing.
Yeah. So that's so basically, so in this simple case, you can see that after scaling, you just get the just because you're going up, going twice this way, and going up once that way. Oh, okay. So this basically triangle. So I guess it's relevant. There's like Hawaii, Easter Island, and New Zealand. Right? Remember that? There's a triangle. Okay. So that's your simple case. And so in general, you can do a similar algorithm for more things. Okay. So finally, we'll get on to the Chebyshev transform. 10 minutes. Okay, so suppose we're given one of these exponents which are in one of these nk's here. So these are grids. Then we can consider so the following quantities which are the analog of Chebyshev constants. Oh, they are Chebyshev constants. yeah, so just write it this way. So T sub K phi, so phi is our weight, K is our convex set, alpha is our, the exponent of our, we're going to be looking at, and that's going to be the inf over, when you take the sup norm of, yeah, so that's right, P e to the minus K phi. So this sup norm over the one that we did before, where P is of the form, it's monic, so it's Z alpha plus dot 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 means higher order things. Okay, so the trading term is 1, coefficient, okay. So here's the proposition, is that you can think of, if you take any point in the interior of the Okunko body, so this limiting thing, then you calculate this limit of these things at the finite stage. So the limit is, say, alpha over k, because we're taking like a 1 over k thing, going to a point in the interior. Sorry, in the interior. Yeah, so this is the Okunko point. T sub k alpha. So the purpose is that this limit exists, and we'll define it to be the T sub k theta, right? So first statement is that the limit exists, so we'll define it to be that. And the second statement is that this function here, if you take phi maps into tau, sorry, the log, so that's a continuous convex function on the interior. So this function here, so that's the Chebyshev transform, this thing. That's the Chebyshev transform. So put all out.
So it maps Akunkov body into something.
It maps the
Interior of Akunkov body into.
Yeah. So it maps the point of the interior of the Akunkov body into. Oh, so this is yeah, it's just a real valued function basically.
Okay.
Yeah. Yeah. So that's positive real value. So this is just yeah, real. Okay. Final thing, how is this thing related with the transfinite diameter that I erased before? Okay, so when we relation to the transfinite diameter. So remember, this thing was defined to be the sort of, let's say, determinant of, all right, E sub alpha is here. Say xi, and basically you're maximizing determinant over points of k, right? So maximize this thing. When you write the determinant, you can always take sort of linear combinations of rows. If you're thinking of the columns indexed by the polynomials and well, and it's sort of like polynomials this way, points that way. Then by taking linear combinations of rows, you can replace, if this is, you can replace any sort of monic basis. So when I say monic, I mean that at the kth stage, you get a basis of this, and it's monic when you write it out as a power series, right? Training times 1. Okay, so for any monic basis, well, you might as well take these monic things here. Okay, so so just write T sub alpha to be, the T's are the ones that attain the inf in this definition of Chebyshev constant here. Okay, when you take the determinant, of course you get, you can make a really bad estimate here, and you just get, say, mk factorial, that's the, how many terms, and you get sort of this alternating sum. But you can just, you know, just estimate everything by taking absolute values, and they'll become positive. The value of this thing here, you can estimate it by these things, right? The subnorm. So you get a really bad estimate, but alright, so let's just write this, k, and then the alpha here, right? But of course, what happens is that when you take the determinant, when looking at the transfinite diameter at the kth stage, you're always taking one of a k mkth root, scaling this thing. So what happens when you do that? Well, what happens is that this thing disappears in the limit. And, oh yeah, so what's this here? Yeah, so I forgot, right, you actually have a product of sort of, you know, MK things, right? In here. So this thing disappears in the limit, and here, if you exponentiate it, you can sort of rewrite it as 1 over kmk times log, right, of those things. And now you can perhaps see where this is heading. This thing now looks like these things in the limit, when k is going to infinity, these are going to these things. The sum is going to go to an integral. It's going to go to an integral. And you've got this normalization here. So in the end, this thing goes to the exponent of 1 over the volume of your Kunkov body, then the integral of the Chebyshev transform, right?
So, okay.
Yeah.
Okay. No.
So log of t.
You know, Kunkov body is basically the difference, measures the difference between algebraic linearity from being linear, algebraically, yes?
Mm-hmm.
Okay, so therefore what we're measuring something like a difference between that and kind of general algebraic, general stability, yeah? Okay. And now you want to give a similar estimate for that through the volumes of the matrix on the space of polynomials, yes? So you try to compare two things.
Yeah.
Okay. One is global, one is local at a point.
Mm-hmm. Right, yeah, so I guess the point is, yeah, like you're saying, I mean, the point could be any point locally, and I'm writing the set here, the k. It could be away, but, you know.
Yeah. And still you can estimate.
Eh?
Your point may not be in k, and still you can do something with p, yeah? So
Yeah,
there is
yeah.
still some relation.
Right. Yes, and in the classical case that this is sort of generalizing is a formula of Zaruta in the 70s, where this point, where you're just looking in Cn, this is a compact set in Cn, but this point is actually hydroplane at infinity, but you're not thinking of it. But in the classical case, this point at infinity, you're not thinking of it as a point, but you're thinking of it as the looking at the degrees, and goes to infinity. Trading term here means leading coefficient over there. So that's the classical, yeah. So it all fits nicely into this framework. Okay, but yeah, that's basically it, except for the fact that this is just a one-sided estimate, right? But the theorem really says that you get equality. So basically what I proved was like a lower bound, using the fact that you are minimal, right? You can get a lower bound and then really get equality in the limit. Yeah, I could do it sort of just analysis this way, but this thing is, this Chebyshev terms were actually defined by Nystrom, but I guess he was more a complex geometer, so he just looked at stuff in, well, I mean, this case was not polynomials, but sort of more a general geometric case, but he was looking at basically the whole, sort of a weight, where K is sort of the whole space in a continuous weight. Yeah. Okay, so that's the final thing. Thank you.
Questions?
Okay, let me try to understand. So you begin with something with, you fix some kind of measure, yeah?
Yeah.
Which is essentially depends on K and some measure on this, maybe compact subset? Do you mean, is it always compact?
No, it doesn't have to be compact. It just has to be closed.
But
yeah.
Closed and measure, but finite measure altogether.
Yes, finite measure.
Some, and then you're trying to build a kind of norm, yes, on the spaces of polynomials and so on. You keep building this global kind of invariance, and then you are comparing nonlinearity at essentially every point. The difference from being linear. This is measured difference from being linear with some global invariance which appear from response. Yes. Okay.
More questions? Okay, if no more questions, let's thank Sione again. And, let's have 10 minutes.